Well, thank you again, Roberto, for your invitation. And well, I'm from Mexico, and currently I'm working as an associate professor here at UNAM, which is the National University of Mexico. And the research that I'm going to present you today was funded by the National Council here in Mexico of Science and Technology. And this is just one of several hazard maps that we have been preparing for the Tacaná Volcanic Complex. And I'm going to talk to you today about the map that we integrated for small volume landslides. And this is a work with many collaborators, and I'm representing those other colleagues. And just to begin, let me share with you the name and where you can find my paper, which is published in Natural Hazards Journal. Here is the DOI, and I think I'm going to use this one. Okay, better. Just to let you know where you can find one of our works. So let's begin by sharing with you where is located the Tacaná Volcanic Complex. I've seen since yesterday that many of you have talked from several types of landslides and several contexts. And well, I'm going to present you a volcanic context. Yes, we made some numerical simulations about an active volcano that you can see here. It's a part of a volcanic chain named the Central America Volcanic Arc, or also known as just Cava, and is the northwesternmost volcano located in this volcanic chain that extends from more than 1,000 kilometers down to South America, actually down to Panama. It begins here in the borderline between Mexico and Guatemala and extends southeast down to Panama. And this volcanic complex is located in a very complex tectonic situation also, because we can see in this part of the map that there's the Middle America Trench, that is a tectonic setting characterized by the subduction between mostly the Cocos and the Caribbean plates. But we also have in here another important tectonic setting, which is set between the movement between the North American plate and the Caribbean plate. And this movement resulting in this Polochic-Motagua fault zone that, as can be seen here, is it's a lateral left strike-slip fault zone that promotes also not only the volcanic activity in this region, but also there is a lot of seismicity within this zone, not only provoked by this situation, by this subduction zone, but also because of the Polochic-Motagua fault zone. And this is where we can find the Tacaná Volcanic Complex. So these two are important features that could lead eventually not only to a future volcanic eruption in the near future, but also to the formation of landslides. And let's talk about the geology of the Tacaná complex. We can see here in this plan view map the general geology of the complex, which is colored in brownish and reddish and yellowish colors. And we can see the complex that is surrounded by other volcanic features as the calderas named Chanjale, San Rafael, and Sirinal. These features actually function as natural barriers for the volcano, which was constructed inside the San Rafael caldera. Now, if we see this profile from northeast to southwest, and from the oldest to the youngest structure, we have the Chichu volcano, the Tacaná volcano, Ardillas Dome, and San Antonio volcano. And actually, San Antonio volcano is the youngest structure of the main complex, but well, it's from the Holocene. But we can see that the Ardillas Dome, that is this little thing right here, and this little bump in this topography. Actually, we're not very sure about the exact age of the Ardillas Dome, because we are supposing that it must be older than 760 years before present, because at this time we found some surge deposits around the summit of the volcano that were produced from an explosive eruption of this age that left deposits all over the summit. And one of our colleagues that also was working with us to obtain this research, he obtained chlorine 36 age for the Ardillas Dome, but he described that this age that was dated in 300 years old, that is a lot more younger than the other structure. He described that that's probably not the emplacement age for the dome. So we are supposing that this structure must be older, because it was intruded between the Tacaná and San Antonio edifices, and it's also covered by the deposits of this explosive eruption. So we can see a zoom in to the summit of the volcano, where we can see the units of the geology of the main structures of this volcanic complex. The Tacaná volcano, as can be seen here, is formed by two, and one of these domes is dissected in two, so it forms like three little domes. The Ardillas Dome that is intruded between these two structures. And we also hear this little polygon colored in blue that we think that it was probably originated by the explosion that left the eruption of 760 years before present. So it is also at one side of the Ardillas Dome. Now, I present you in this scheme a summary of the main volcanic processes that have taken place within the Tacaná Volcanic Complex. We have found in the surroundings of the edifice at least 11 pyroclastic density currents, or at least 11 deposits associated with different types of pyroclastic density current, mostly block and ash flows, which are signaled as BAFT. We have also mapped at least 6 Plinian to subplinian type eruptions that have left very sparse deposits of asphalt deposits, I mean. And we have also found several stages of effusive activity characterized by 25 lava flows. What we have encountered also are 5 big deposits of debris avalanches and at least 2 events that have developed syneruptive lahars during the entire history of the Tacaná Volcanic Complex. We can see from this scheme that most of this activity has concentrated at the Tacaná edifice. Okay, but the main thing about this research is the Ardillas Dome. And we can see from this map the structural features, I mean the fractures and the fissures and the faults that are currently dissecting the volcanic edifice. And we can see that the main orientation of these features are consistent with the same orientation as the volcanic complex main edifices, which is northeast, southwest. And let's focus within this area, which is marking this collapsed scar from the Ardillas Dome. We can see from this photograph that was taken from southwest towards the summit of the complex, and we can see within these yellow lines the top of the Ardillas Dome, which is located in here. And these are some features that are marking this zone that is breaking up. I mean, it's half fault and half fractures that are dissecting the Ardillas Dome. And this is the main direction, which is towards the southeast. And it's opening the surface of the main part of the dome, and it's going towards this direction. We can also hear, we can see here also from this photograph the little crater lake that was formed due to the 760 years explosive eruption. And we can also point it out within this photograph the site of one of the most recent eruptions that has been taking place within the complex. I mean, we have 2 phreatic explosions atop of the Tacaná volcano. The first one in 1949 and the other one in 1986 that was situated down here, right in the scarp of a previous collapse of the main edifice. So all these features are, as we can see here, aligned or are mainly controlled by the structural features that we can see from this aerial view of the volcano. Now, this is the main objective of the research that I'm presenting you today, because during the field campaigns, we detected within this area a surface that could be prone to be detached from the main Ardillas Dome and potentially could form a landslide. So we detected this from our field campaigns. From this other view, we can see the shape of this surface that we calculate the maximum volume that could be detached from this zone. This is the shape and the size of this surface. And we detected also that you can see here, this is the beginning of a very narrow and deep ravine that is called Maxam Ravine. And this is a photograph from an active debris and rockfall zone that we detected just at top of here, at top of the Maxam Ravine. And all these conditions give us the reasons why we started to do this research, because we detected that right now there is an active zone that is having rockfalls and have all these debris from the vegetation. And this site is characterized not only from these structural features, but also we have superficial hydrothermal alteration that is taking place all around the summit of the volcano. So we have a lot of debris that could still accumulate within this part or even downflow the Maxon ravine. So what we did was to perform a series of numerical simulations of this zone that could be detached from the southeastern side of the Ardillas Dome. And we estimate using the 3D analysis tools from ArcMap of Esri, a maximum volume of 25 million cubic meters of material that could be detached and to form a landslide. And for the landslide modeling, we decide to use the Titan 2D model, which was developed by the research group of Pittman and Patra and colleagues at the University of Buffalo. And this is a depth average model based on frictional Moore-Coulomb behavior for shallow water granular flows in order to simulate the formation of future landslides sourced within this zone. So first, what we did was to perform a sensitivity analysis in which we used digital elevation model as input of 5 meter pixel resolution. We distributed these 5 source points along the main fractures and fissures that we detected that could be the starting point of a landslide within this zone. And we also varied the amount of material, I mean the volumes, from possible landslides. And I want to explain that the maximum volume simulated was this value that we obtained with the ArcMap tools of 25 million cubic meters, but we also decide to simulate volumes with a lesser volume. We ranged these volumes from 100,000 cubic meters up to 25 million cubic meters. And for the other input parameters, we decide to maintain the internal friction angle and the basal friction angle, as well as these input parameters within all the simulations the same, because these values were obtained from the calibration of this model in a previous work made by me and my colleagues for block and ash flows and debris avalanches, also simulated around the Tacaná Volcanic Complex. So with these values and the variation of these input parameters, we start to modeling future landslides originated within this zone. So let me show you some of our results. First, in these maps, we can see the outcomes from the first series of simulation, where we decide to use the same input volume, which was 100,000 cubic meters, and we vary, as we can see here, the input source. These input sources, these point sources that are distributed within this zone, we vary the point where the landslide was about to begin during the simulation. And we noticed from this first set of simulations that if we maintain the same volume in all those cases, but instead we move the source origin for the landslide, the outcomes did not vary much. I mean, we can observe from this set of simulations that the outcomes are similar. I mean, the maximum distance reached by the landslide was about 4 kilometers, covering an area of 1 square kilometer, and reaching at the post depth within the Maxam ravine of 6 plus minus 0.2 meters in all the cases. So the source point was not so sensitive as we can see from this result. But second, on a second part, on a second set of simulations, we obtained these maps where we can observe that letting the same source point but varying the input volume from the smallest volume that was 100,000 cubic meters up to 25 million cubic meters, we can observe that the results vary a lot. I mean, if we increase the amount of volume involved within the landslide, the surface impacted or affected downflow by the landslide was bigger, obviously. But if we only observe the three first maps, one of the main outcomes that we can observe is that there's still the biggest part of the landslide is delimited to the topography of the Maxam ravine. But when we reach the simulation where we involve an input volume bigger than 2.5 million cubic meters, part of the material associated with the landslide begins to expand or to distribute to some other parts outside of the ravine. We also can observe that the maximum length, the maximum depth, and the surface covered by this simulated landslide will vary according to the simulated volume. So this is the main input parameter that affects the outputs of the model, as we observed this behavior before while using the Titan 2D model. And with these results, we also perform an analysis of the potential damage that the biggest landslide that we simulate could do to the localities settled in the southern flank of the volcano, which is the most impacted with considering this scenario. We consider this scenario the source point B, which is the tallest, with the biggest volume simulated as the worst case scenario from all the simulations that we run. And this analysis, we perform it based on the intensity index for debris flows that was proposed by Jacob and colleagues in 2012, and is based on the expected depth and the maximum flow velocity in that case for debris flow but in this case for landslides. And within this index, we can estimate the sort of impact force of the landslide. And those authors propose probability matrix, well, damage class probability matrix, where they classified according to the level of destruction or the impact done to the buildings, the level of losses that those buildings could have. So we use this model using the values that we obtain from our simulation, from this worst case simulation, where we can see that impacted at least 8 villages. They're in pale blue. And we obtain a map for the intensity index that we represented on a color scale from yellow to red. And according just to this map, at least 5 villages will suffer some sedimentation, which is colored within the yellow zone. 2 villages will endure some structural damage that are distributed within the orange zone, and 1 village will have major structural damages that are inside the red zone. But while we were doing this analysis and we compare the probability matrix that we obtained with the depth and velocity values according to the distribution map to the distribution of the intensity index within this map, we observe mostly that there are some inconsistencies between the values obtained from the metrics and what we can observe from the distribution of the deposit left by the landslide. And we are thinking that probably these inconsistencies are due to some uncertainties associated with the estimation of the exact velocity of impact of the flow. I mean, we can obtain a very certain velocity value mostly inside of the ravine, where the model is calibrated. But in these areas where the fine particles of the landslide could surpass a high topography, in those places, like in here, the level of certainty about the calculation of the velocity of impact is not that well estimated by the model. So we have some level of uncertainty in some of these zones that we think that probably is because of that the values that we obtain from this probability matrix compared to the map do not match that well. But it's an approach that we're still working on to enhance our results and the maps that we obtain. But the main objective of this kind of maps is that we can see the distribution of the deposit that we can left a very big landslide, where it will affect at least 8 villages, and within these villages lives more than 2,000 persons. And within these villages, there are also constructed at least 370 dwellings that could be impacted in some extent by a landslide like the one we're showing here. So some aspects to discuss. Well, as I already mentioned it, the volume of the surface prone to be detached in the southeastern side of the Ardillas Dome could have been overestimated due to the methodology that we use for its calculation. The tools that are set within the 3D analyst module of ArcMap uses the volumetric difference between two surface models. So this surface could be could have been not placed in the right place to estimate the volume at top of this surface. So we are aware that probably we overestimated this volume. So this is why actually we decided to simulate landslides of minor volumes with a minor volume of material involved. And from the sensitivity analysis performed to the model, we also observe, as we show you in the maps, that the input volume is the input parameter that has the biggest effect on the behavior of the simulated flow that we obtain, especially in the impact on in the longitude or the size of the impacted area and the maximum distance reached by the flows. We also observe this fact that in those landslides involving volumes bigger than 2.5 million cubic meters, just those landslides bigger than this value will surpass the narrow topography of the Maxan ravine, and actually it will also surpass a ridge that is located south of the Chichut volcano, which is a relief or a characteristic of the morphology of the volcano that naturally should serve as a barrier for those villages settled in the back of this ridge. But due to the location of the source of the surface that could be prone to be detached, that is very steep, even landslides involving more than 2.5 million cubic meters material could surpass this ridge and affect the villages that are settled in this backside of this ridge. And actually, within this ridge is located a village named Chiquihuite. This is important, and in a few slides, I'm going to show you why. And finally, the last aspect to discuss is that the intensity index analysis that I just showed you in the last map, we detect these inconsistencies between the index reflected in the map and the classification obtained from the probability matrix. And as I just explained to you, this could be due to the uncertainties associated with the estimation of especially the velocity. It could be also due to the estimation of the expected flow depth, but mostly because of the maximum flow velocity estimated by the model, but in those sites where are located the villages that could be impacted by the landslide. And as a conclusion, our conclusions are very important because we now have a better understanding about how landslides of different sizes, from small to a bigger size, would distribute downflow. I mean, in the down flanks of the volcano, where lives at least 2,000 people. And from our maps, we observe that there will be some sites or some areas that a landslide could reach flow depths bigger than 6 meters and have impacting velocity of more than 5.7 meters per second. And we also observe from this distribution of the deposits that the villages that could be impacted due to the materials of the dwellings that were constructed within these villages, we are certain that the potential damage to those structures will be important, because according to our map, we estimate that at least one locality will have some sedimentation, and according to according to the matrix that I just showed you here, we have discrepancies, but in this case, the probability matrix give us as a result that at least 2 of the villages impacted by the biggest landslide will be completely destroyed. And probably we cannot see these villages completely destroyed within our map, but we are certain that a landslide coming from the source in the Ardillas Dome, southeastern side, will affect the villages located downflow. And the situation that is currently present within these villages, within these communities, is that the materials of the buildings that they have constructed, or the houses that they have constructed, will not resist a landslide, no matter how the amount of volume involved in the landslide. And we must also consider that the Tacaná Volcanic Complex setting is characterized by one of the heaviest is located in one of the regions that almost all the years have heavy rainfalls, and this has developed a high superficial hydrothermal alteration. And as we can observe from the photographies that I just showed you, the morphology at top of the volcano is very steep and is currently being dissected by these structural features as faults and fissures and fractures. And as I described at the beginning of my talk, it is a region of active seismicity because of the tectonic setting around the volcano. So probably not just the Ardillas Dome, but all the complex itself has a high potential to develop landslides of different volumes that, considering the number of inhabitants that are currently living in the flanks of the volcano, we are aware that this area could, in the future, help with disasters, and disasters like the one that just happened last year. I don't know if you can see this video, but if not, you can see here a very small landslide. It was a video, sorry, but this was a very small landslide that took place during the rainy season of the last year, during September. And this community is the village named Chiquihuite. So due to the extreme rainfalls that were associated to a hurricane, part of the mountain developed a small landslide that at least devastated 3 small houses that were in the limits of the main community of Chiquihuite. Oh, now you can see. So we heard from this disaster last year, months after our research paper was published. So we're not that wrong studying this type of phenomena at Tacaná volcano. And lastly, I show you within this map the other potential detachment surfaces that we have detected around the summit of the volcano and in the lower parts of the edifices. And just to tell you, the Chiquihuite community is settled right here, and the landslide that destroyed those little houses begin from here in a very low slope of the volcano. So we're considering that the main sources of landslides involving bigger volumes could be detached from the upper part of the volcano because of all of these conditions. And well, that's it. Thank you for your attention.